Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Our distinguished guest tonight is David Kaiser of Massachusetts Institute of Technology, where he is the Germeshausen Professor of History of Science, the Director of the Program in Science, Technology, and Society, and Senior Lecturer in the Department of Physics. He is also an MIT McVicker Faculty Fellow. Dr. Kaiser received 2 PhDs from Harvard University, one in physics and the other in the history of science. He joined the MIT faculty in 2000 and became director of the program in Science, Technology, and Society in 2011. David Kaiser has 2 areas of research, history and physics. His historical research focuses on the development of physics in the United States during the Cold War, specifically on how physics was influenced by the politics and culture of that time. His physics research is on early universe cosmology, working at the interface of particle physics and gravitation. Dr. Kaiser has produced a number of award-winning books, including the very popular How the Hippies Saved Physics. He's an elected fellow of the American Physical Society and an editor of the journal Historical Studies in the Natural Sciences. He's received numerous honors for his work, and he's been featured in many magazine articles and also American and British public radio programs. Tonight, Dr. Kaiser discusses the relationship between political eras and the development of critical advances in physics. He'll also tell us about his current work on the early universe. It's a very special honor to welcome David Kaiser. Welcome, sir.
Thank you so much. Thanks for having me.
We usually think of science as sort of out there, right, isolated, but you put it squarely in a culture.
Yeah.
Can you give us some ideas about it?
Sure. It's a very big topic, and so that's part of the fun, is that we'll never run out of examples. But you're right. I think many people have a notion of science as being somehow separate from, so to speak, the real world or the daily lives of ordinary people. And so it's been very fascinating as an historian to discover ways in which scientists and scientific knowledge making was not only sort of separated, but was really sort of thoroughly of its time and place, and that we can see signs of that we can see traces in which it was really deeply embedded as part of that world, not separate from it. And so one of the things that I find fun is to think about different examples of what should be sort of the same activity. We think, well, how do, say, theoretical physicists go about their daily job? And then we can start seeing really quite interesting differences in how they do that over a pretty short span of time. We don't have to go all the way back very far deep in the past in history or to the far-flung reaches of the globe. We can look even, say, in the United States over the last several decades, or compare, say, Britain and the U.S., places that look kind of similar in many ways. And yet we can see pretty dramatic changes in how people have assumed they should do their job. What did they think it was to be, say, a scientist or a physicist in those times and places? One of my favorite books, actually, that got me thinking about this some years ago is by a colleague, Andy Warwick, who's an historian, very gifted historian. And he wrote a fascinating book on the making of young scientists in Cambridge University in the UK over the sort of 19th century, long 19th century. And for much of that period, or certainly for many decades, every single undergraduate student at Cambridge University had to prove themselves by taking an enormously complicated exam in pure mathematics. I mean, it sounds like a torture instrument today. We can't do that, right? And not only was it a very, very rigorous exam itself, but they published the rank-ordered list of every sort of graduate in the national newspapers. So, I mean, imagine how that felt. And there were, mental breakdowns and all the human dramas you might expect. And the idea was that Cambridge and Britain more broadly was not aiming to make 10,000 mathematical physicists, not at all. The goal at the time was to produce what they considered kind of disciplined, nimble minds who could run the empire. This was the era when, as the saying went, the sun never set on the British Empire. And so the idea was if you could prove yourself by doing incredibly hard calculus problems, then you were clearly fit to run the office in India or to join the Anglican clergy or whatever. And so Andy has this amazing way of showing how the assumptions about what higher education, what learning should be all about, really sets in motion, sets in train a series of these reforms. So we have a very, to our eyes, kind of strange-looking elite, incredibly powerful institution that looks, that bears the marks of time and place, right? So they trained people, very smart people, very well there in ways that don't make any sense to us, today, and didn't make sense in other France at the time. So there are examples like that where we don't have to go too far away to find places where it's not that society has sort of intervened and messed up what would have otherwise been very good science. Elite world-class science gets done in curious kind of place-specific ways, time-specific ways. Anyway, that's something that just really captured me, even as a young student, to think about, I'm, as a college student, I was learning certain things in certain ways and working very hard at my homework assignments, as college students do most of the time. And then to realize that was what seemed so second nature, so it had to be that way, was really, modeled of a very particular moment in time.
Right.
So.
And this has broken down at different times. The Greeks at a certain period broke all the rules, I guess, and maybe in other cases, and we're leading up to your most wonderful example of this in the United States. But before we go back to this, I'd like to ask you about how culture influenced scientists' thinking in some ways too, particularly in biases to prove racism and so on.
Sure, yes. Well, no, unfortunately, as you know, there's no shortage of examples where, again, from where we sit today, it's easier to see what clearly when things went wrong.
Yeah.
And there's a very rich history, alas, of what's often called scientific racism, or seemingly scientifically based theories of human origins and human difference, which today we can see was shot through with bias and assumptions of the age that most of us would not put stock in today, even though these ideas were put forward by often very earnest, very smart, well-educated people. So there's unfortunately a long litany of these examples, and again, not just from long ago or far away. And what fascinates me is to turn it around and see all the examples of really wonderful science that we still hold up as exemplary today, that was no more outside of society than those quite egregious examples were. So I don't see it as a kind of Garden of Eden where there's a kind of pure science untouched by the kind of it's almost like a biblical narrative, a kind of a lapsarian, like we've been pushed out of a pure land. I don't think we were ever in a kind of pure land. And so that becomes the job of the historians, and in some sense the broader public at large, to try to understand how are these ideas fitting together, making sense, given the kind of ideas and resources at hand, and that those don't stay constant; those change over time. And so there are, as I say, horrible examples, as well as, when we look back, examples of science that we still hold up and teach our students and think is just wonderful, still came from very specific kind of cultural and institutional moments. Right.
Another thing there is, we were talking a little while ago about the slow emergence of real science out of more mystical kinds of thinking, and we were talking about very great scientists like Newton and so on. And this was the nature of science, at least in the West, that it came about in this slow progress. Would you say that that's true of a lot of the sciences? Was true in physics and that it came out?
I certainly would. And Newton's a wonderful example. Newton was, just a remarkably fascinating and complicated figure. And now that's going back a couple hundred years, so we could sometimes we can comfort ourselves. Oh, well, that was the bad old days, and now, of course, we know we're so modern and we know what's what. But there are examples that are much closer to our own backyard of extremely talented and, again, sort of smart and earnest and hardworking scientists, who much of whose work we still admire and teach, who nonetheless were convinced in their day that either their favorite ideas led them to certain conclusions, which we now no longer would see that connection, or their work was inspired by ideas that we might consider, mythical or occult or somehow beyond the pale.
Right.
And that's not just Newton. It's not just, say, James Clerk Maxwell,
right?
Dirac, or Niels Bohr, or
yes,
Schrödinger,
it goes on and on, doesn't it?
Long list. That's right. And so that's another maybe a nice example of how the scientists, of course, are people, they're humans living in a time and place, and that I think accounts for the great richness of science. I don't think that's a problem to be solved. I think that's just how the world has been and still is.
Yes, which leads us to this book, How the Hippies Saved Physics. And you have pointed out here, I mean, this is the thrust of the book, that these people were really out there, in so many ways, and persisted with this, and yet the peculiarities of this time led to an enormous breakthrough. Would you step us through that? I believe that you were arguing that it was really the peculiarities of the time, and you got this sort of thing, and people were able to explore something they hadn't. Well, anyway.
Yeah, no, I think that's right, and that's part of why this time period is so fascinating. I mean, it's a kind of colorful period in American history.
Right.
The sort of late 1960s, early 1970s, it was a whirlwind. I mean, I was barely there, but I'm an historian, so I've been able to read and talk with people who were more there. So it's a remarkable period for how the United States was changing, and the comparable developments in many parts of the world as well. Politically and culturally, with the various kind of long 60s revolutions that we now can sort of tick off one after the other, but also intellectually, in this case, in certain areas of science and physics and so on. So what fascinated me about this group that I wound up writing about, they called themselves the Fundamental Physics Group. It was very playful. They spelled physics with an F. I would say physics students then as now never learned how to spell, but they were doing it on purpose. And they were a remarkable collection of people, on the order of about 10 kind of core members of that group, who found each other in the early mid-1970s in Berkeley, California, kind of epicenter. Where else, exactly. Epicenter for this kind of New Age movement in North America. And what really grabbed me about them was that they were exquisitely well trained. I mean, they had PhDs in physics from some of the finest programs in the United States. They'd done their problem sets. Many of them had published in a very good, we might say, mainstream work in the scientific journals along the way. And then they sort of hit the job market when the bottom fell out. This is one way where we see a very blunt version of society busting into ordinary science. So between the late 60s and early 1970s, many fields in academia, but physics hardest of all, went through a very rapid change. The bottom fell out, basically. So physics had been growing faster than any other field after World War II, on the heels of these dramatic wartime projects like the atomic bomb and radar and many other smaller projects. Every field grew rapidly after World War II with the influx of new students and the GI Bill and all the rest. Physics outpaced them all. Almost every field went through some sort of contraction around 1970, give or take, and none fell deeper, harder, faster than physics. It just was this huge bellwether for larger changes in the American Academy at the time. And
where does a physicist go?
And where does it go? Many of them, or some of them, chose to go to California and sort of do what they could. And what they couldn't do, for the most part, was follow a kind of familiar career path. The jobs dried up very rapidly, much more rapidly than the student numbers did. There was a huge mismatch of really thousands of extremely talented, very well-trained young people in physics, engineering, mathematics, many allied fields, who had gone into the field with dreams of an academic career, were told by the federal government that the nation needed many more scientists and engineers in the Sputnik era, and then the sort of jobs simply weren't there when they were done. And that was true especially of the folks I wound up writing most about. So they were sort of at the wrong place at the wrong time. So they kind of bumble along through different accidents of history and biography sort of bring them together in Berkeley in the early 70s, and they find each other. And what captivated me was that they had this exquisitely strong discipline and training. They had done their PhDs and done extremely good work, and were suddenly kind of thrust out of a kind of comfort zone or an expected path, the one of the sort that they certainly had anticipated or been looking forward to. And so they became actually, I guess today we'd call them very entrepreneurial. I mean, they really sort of made do with what they had and were very creative in creating a kind of parallel universe to the kind of institutions or structures that would have been familiar at the time for doing science. So they found their own ways to support the research. And even theoretical research is expensive because you have to eat sometimes, right? You have to pay rent.
Yeah.
Exactly, right. So they found their own patrons. They found their own ways to sort of share their ideas amongst themselves as well as disseminate their work in very creative, sometimes very effective, but kind of off the beaten path sorts of ways. And so on. So they made a kind of, almost like a parallel universe to the kind of modern university. And so they combined this, a certain kind of rigor with, and discipline and training with a very kind of, in some cases, free-spirited, fun-loving, not highly structured, hippie kind of creativity, being open to some pretty strange-sounding ideas. Yeah.
Yes. What kinds of ideas?
It's a delicious menu. So, I mean, so on the one hand, it included, for some members, not all, but for some, it included things like ESP and spoon bending, which was
the Geller thing, right?
Like Uri Geller, most famously in that time period. That there was, this wasn't only the stuff of kind of small underground boutique-y newsletters. This is the front page of the major newspapers. The New York Times ran articles on this, the San Francisco Chronicle did, as well as the Berkeley Barb. I mean, it really was sort of spanning the types of newspapers or sort of media. So that really was literally front page news, especially in the Bay Area in that time. And some of these folks were really excited about that. Were either curious or true believers, or sometimes true believers and very deep skeptics. Sometimes they'd oscillate. But they couldn't kind of avoid it. This was really just in their face in that time and place. And on the other hand, they were also, to a person, deeply fascinated by some of these kind of grand mysteries of modern physics. Some that still fascinate me and my students and many in between. Topics at the heart of quantum theory, some very strange ideas in relativity. And what was really sort of fun about this time period is that for some members, not all, for some members of that group, they began to wonder if there were connections between these different areas.
That was a point you made really well. I wanted to make that clear.
And so to some people, these were two sets of curious ideas, and it stopped there. To others, maybe sort of the weirdnesses of quantum theory, which no matter how we slice it, they can sound awfully weird or certainly counterintuitive. Maybe those actually could account for, maybe that explained the strangenesses of, say, accounts of ESP or other seemingly occult phenomena. And so is that any stranger than other kind of strange and magical effects that were eventually brought within the fold of mainstream science? I mean, not all that much longer ago, a couple centuries, magnetism seemed like, the stuff of spirits and the gods. How could this strange effect be happening? And now we'd say there's nothing spooky. We understand something about magnetic fields. And so many of these folks wondered, is this the next thing? Are these strange notions of kind of consciousness and its possible powers in the world, or in some cases, reputed powers in the world, are those the next set of phenomena that today seem spooky and tomorrow will seem tamed? And they were not alone in thinking that.
Oh, it was very popular at that time. All this paranormal stuff was very popular.
It was. And what they had was, let's say, training and inklings and curiosity in first principles foundational physics. And an openness to some of these other topics as well. And that was a very, and they were doing it outside the ordinary kind of university environment for the most part. And so it was a very creative, kind of free-flowing hodgepodge.
In a university setting, would that have been a bit more difficult? Like if you were in your physics, would these people have been able to talk about this in a physics class the way that they were talking about in fundamental physics group?
So it would not have been easy. It also would not have been impossible. There were some folks I wrote about briefly here. They were this group was tethered to not just mainstream but often very elite physics. A few kind of senior figures in the field shared at least an openness or a curiosity. Rarely would they share the kind of enthusiasms, but they would say, well, this is curious, and physicists need to be open to all things. Now, that was by no means the norm, but there were some. And so there was, at the time, the department head of the very prestigious department at Columbia University, Department of Physics, was at least open to some questions. He was by no means endorsing this, but saying, well, maybe. And there were a few other people like that dotted around. It was not mainstream stuff, and nor am I saying it should have been. This is not a judgment thing, but just looking at who was doing what where. It was certainly not the stuff of classroom discussion. There were pockets. There were nodes to whom they could be connected.
Okay.
Yeah.
Now, these people were all interested in quantum mechanics generally, but this developed into something. And if I follow you correctly, it seems as though this really was a chain. That is, it was sort of causative, that they were, as you said, well-trained, open to some really complicated stuff, but having this kind of mentality at that time was sort of fertile ground for developing a really important breakthrough, I think.
Yes.
What was that? How did this work?
Yeah, so they were really captivated, among other things, by something that we now call Bell's Theorem, or quantum entanglement, sort of synonymous at this point.
Well, that makes sense, doesn't it? Entanglement with the psychic stuff, right?
That was exactly what some of them thought would be the bridge, exactly. And entanglement is really can sound very spooky. In fact, Albert Einstein had wondered about this notion even before John Bell's work had come along, and he dismissed it as what he called spooky actions at a distance. That was not meant to be a compliment. This is just horrible. Einstein, by that point, was a really very trenchant critic of quantum theory. And he would say to his colleagues, if your equations predicted that kind of nonsense, then clearly that's your problem. Nature can't possibly be that strange. You've made a mistake. That was Einstein's decided view. Now most would think that he lost that one. He got a lot of things right, not everything right. But nonetheless, it does heighten the fact that this sounds awfully unusual or counterintuitive.
What is entanglement?
Yeah. So entanglement, it's one of the fun things I had most fun in writing the book was trying to figure out how to describe entanglement.
Yeah.
And first I thought I would just offload that to my friends, how my friends describe entanglement. That didn't help. There are some wonderful metaphors people have developed. They get increasingly kind of Byzantine. But it only accentuates the fact that it really is a challenge to put it into kind of ordinary language. So here's one try. Entanglement concerns certain kinds of systems, quantum, say pairs of quantum particles, that could be prepared a certain way. They could say be shot out from a source. They have a common origin, and some source, sort of like a radioactive source, not so bizarre, could spit out pairs of particles. The strangeness comes when we try to describe what's going to happen to particle B, given what we know has to happen to particle A. What it really boils down to is that it's, according to quantum theory at least, it's impossible to give a description of particle B without referring in a very concrete way to particle A, that their fates are linked, to speak metaphorically. There's no way to describe a self-contained description of particle B that doesn't also already include something about what happens over here. So that starts to sound like if I do something here, it should have an effect over there.
Immediately, right?
According to the equations, it should be an instant kind of connection of some vague sort. John Bell himself, a marvelous, a very, very creative and talented physicist who helped kind of clarify this in 1964. We just celebrated the 50th anniversary of this work recently. He actually shared ideas much like Einstein's. He thought this sounds kind of weird. So he was the one who upped the ante and showed that this was an inescapable prediction from quantum theory. It wasn't so clear, was this, did the equations require that, or was it a misunderstanding? John Bell, among other things, clarified that this really is a hard prediction for quantum theory. And then the question was, well, is that true of the world, or is that just true on our scratch pads? That the behavior of these two particles is indeed somehow deeply entwined, inescapably entwined, if quantum theory is right. And Bell, frankly, hoped it would not. He hoped there would be a view more like Einstein's, as he wrote many times later in life. So it does sound spooky, and it sounds like what I do here could possibly have an impact over there, faster than the speed of light, faster than ordinary messages could have traveled between us. And then, as you say, if one is immersed in Berkeley in 1975, and on the front page of the regular newspapers, there's stories about ESP and telekinesis, and now you're thinking
bending
about
spoons and everything,
and we're all connected in World One.
Right.
You can see very quickly
Yes.
this might be heightened as a topic of real curiosity.
Yeah.
That's right.
Yeah. What was the upshot of this?
So I should say, quantum mechanics by this point was very, very well accepted. And in fact, every physics student had to take multiple courses in quantum mechanics. Quantum mechanics was at the heart of the mainstream by this period, really by the 1950s and certainly by the 60s and 70s. But these weirder elements, these things like Bell's theorem and quantum entanglement, those were not in the textbooks. Those were not what was taught in the ordinary students' training. So, as I say, John Bell derived this very elegant proof that one can't escape this kind of behavior, at least within quantum theory. That was in 1964. Almost a decade, or the better part of a decade went by before most physicists even took notice. Some of the first to take notice, in fact, were these folks that I wound up writing about, who were well ahead of the curve. We'd call them like early adopters today. That they saw this was fascinating, and it really seemed to point to some of the deepest, juiciest questions of, what's the world made of? How does the world work? The kinds of questions that had got them excited as young people in physics in the first place. The questions that got me excited about physics as a young person, for that matter. And yet we're not part of the ordinary curriculum, not in the textbooks by that time. And so they were among the first to say, there's something here. This really is, it is counterintuitive, it's strange, and yet, we have the tools to try to pursue it. Especially for them, one of the things that they were hooked on was this seeming faster than light question. Now, if I do something to particle A here, does its twin respond really faster than light could have traveled? Is it really instantaneous? I often make the joke that, if you tell a bunch of physicists that something happens faster than light, it makes the hairs stand on end. I mean, for me, you couldn't tell, of course, but this is it's not supposed to happen since relativity. Nothing should be able to travel faster than light. No physical force or effect should be instantaneous. And here it is at the cornerstone of modern physics, this proof that at least the equations suggest this is an inescapable consequence. So it looks like we're on a collision course. We have two major pillars for modern physics: relativity, which sets the sort of speed limit, the speed of light, and then quantum theory, which is at least skirting around that. It's certainly pointing to some curious kinds of long-distance connections. And so members of this group, some of them because they thought it would crack the nature of consciousness, some of them because they thought it was just a juicy problem and sort of everywhere in between, really hammered, really drilled on that. Is quantum theory compatible with relativity? Does something like entanglement sort of fight the other grand pillar? Is the whole edifice, about to shake down, or is there some very subtle way that they'll fit together? And so they developed a series of thought experiments, very clever ones, I think. A whole series of them, more and more kind of almost Rube Goldberg kind of clever bells and whistles, to try to harness this effect from quantum theory to beat relativity. If this quantum effect is real, and there was more and more reason to think it was real, then could you harness that to send signals faster than light? Could you affect something over here faster than over here? Let alone could you then explain telekinesis? But just in general, could we get parts of physics to fight, basically? And some of the first examples other people were able to say, oh no, there's a loophole. Oh, you missed this very subtle point. These were not trivial errors. They were what I like now to call productive mistakes. I mean, even the authors of these ideas, these so-called hippies, they'll admit they were mistakes, but they were very, very juicy ones, very subtle ones. The kind that figuring out what went wrong is itself educational. Right? That's the best kind of, maybe we all make such mistakes.
Exactly.
Right? Einstein made these sort of mistakes, Richard Feynman made these, that's the best kind of mistake to make, it seems to me. And these folks were finding very clever sort of tests, trials, and then often it was some members of the group, often other people, who would finally sort of shoot them down, show why they won't work as advertised. And so there was a kind of cat and mouse game. To say, well, okay, you found that my first design wouldn't work to harness this feature of quantum theory, but what about this one? I've now countered your concern there. And that went on for many years and got, it was very playful, done with a great spirit of fun and kind of intellectual adventure, and really led to insights that we all now take for granted, insights that are into the opening pages of some of our new textbooks in quantum theory, that in fact there is a kind of a peaceful coexistence between quantum entanglement and relativity, and we now know why they fit together. They don't fight each other. thanks to the efforts of this group and their dialogue partners.
Right.
It wasn't only them, but they were really instigators.
Right.
Yeah.
Did this lead also to the development of quantum information theory and the idea of quantum for communication?
It did. So it indirectly. I mean, certainly it's a sprawling topic with by now tens of thousands of researchers around the world, many of them at MIT, but really everywhere now. So the argument I'm making is certainly not that these folks invented quantum information science. There are a couple important steps in between. But the ideas they were wrestling with, and mostly the incredible creativity to shoot those ideas down, to show that those were productive mistakes. Productive, yes, but they were mistakes. The reason their ideas would not work, those had, we might now say, very lucky unintended consequences, because we now use those intellectual tools to design things like quantum encryption, quantum teleportation, and all the rest.
Right.
So this group, on the one hand, they were, as I say, they kind of helped discover Bell's theorem or quantum entanglement at all. This was really not a mainstream topic, and they pushed and pushed and pushed and helped bring attention to it and helped get other people to pay attention, and that already is I think, a great good thing. And this notion of quantum entanglement or entangled states, that really is the from which all these wonderful new next generation devices will come. Quantum computing depends at step one on sort of the reality of quantum entanglement. Quantum encryption, quantum teleportation. So these folks helped bring attention to Bell's theorem at all. And then even when you get to the real nitty-gritty, the real finer points of how does entanglement work on its own right, what are the limits, how does it obey relativity, even though on the face it looks like they're headed for conflict, those also now are like wired into our protocols for, say, quantum encryption. So those didn't come only from these folks. These folks pushed and pushed and said, this is really interesting and important and juicy.
Right.
And then more and more people then indeed
But it seemed like they opened the gates in so many ways by doing a lot of work around it that might have been more difficult.
I think they did. And
delayed if they hadn't.
Certainly, right. I think that's fair to say. And among the things they did is they helped smuggle this back into classrooms. So this had not been in the classrooms when they were students or their peers. But they both wrote the first kind of lesson plans or helped inspire, worked with the people who wrote the first lesson plans. And some of their books that went on to become bestsellers that were not written to be textbooks actually had a kind of second life in the classroom.
Isn't that interesting?
So so they were, and these books were often very well positively received in the mainstream physics community. After years had passed. They were on the syllabi, when I was a student many years later.
How about
as
that?
Supplementary reading. But they're real resources.
Yeah.
And so in that sense, I think they did help to plant the seeds. They're not. They don't deserve all the credit. They deserve some. They really were at it.
Quite a few got major prizes, didn't they?
Their books have done well.
Yeah. I was Aspect?
And John Clauser is really one of the first who did share this wonderful, wonderful prize called the Wolf Prize.
That was
as recently as 2010. Which is often seen as the kind of step before the Nobel Prize, and I hope that's true in this case. I think it would be great, certainly well-deserved for Clauser, Alain Aspect, and then Anton Zeilinger. If, say, that trio shared it, I think it's overdue, in my opinion. Yeah.
But a tremendous breakthrough in any case. Now, there's one more thing about this group before we leave it. They were associated with some pretty weird institutes and the CIA.
Yes.
Was this just because we need funding and they took it where they could get it?
Well, I don't think it was just that. I mean, partly it was this entrepreneurial side. You're certainly right. They were, they weren't applying to the NSF, the National Science Foundation, for the most part. And so they did need resources, very modest resources. And on the other hand, the CIA in some sense came to them, or to people with whom they were associated. And that again goes to this kind of cultural moment. There were all these, at one time, highly classified intelligence reports, many of them released through Freedom of Information Act years later, where, independent of this activity, analysts in the Defense Intelligence Agency, the DIA, which was actually within the Pentagon, and then also within the CIA, which is similar but sort of separate agency, some of them became convinced that the Soviets were way ahead of us in mind wars. I mean, how do you ever? I was say the same thing. How did you get resources in the Cold War? You just say the Soviets were doing more of it.
Yeah, and then you got your
and
yes,
then the heavens opened.
Exactly.
And there were reports that we now know of throughout the early 1970s that alleged that the Soviets were pouring enormous resources into mind reading and perhaps mind control. Think about older films like The Manchurian Candidate.
Yes.
I mean, this was again of the moment, of the time. And so some members of these intelligence agencies actually approached researchers who had interests in these areas and said, in effect, your nation needs you. It's time to invest in things like ESP. And all the better if some physicists said, well, they might have an actual explanation, whether it's from entanglement or something else. So the money did indeed start rolling. And as far as we can tell now, there are upwards of $25 million spent on that over, say, a 20-year period. And that is real money. It's sort of rounding errors. It's chump change compared to, say, defense appropriations.
I should say. Right.
And so this was money that was often done kind of discretionary. This was not subject to large peer review or oversight. It was large money in absolute terms, small money compared to the kind of big ticket items that might have invited more oversight. So there was a long-standing program. That's right.
You mentioned also that this had a real influence on subsequent training, educated, the way scientists are trained. And of course, we're in the middle of how many countries are in the middle of this dilemma of how to train students, just in K-12, not just in science and math generally.
Right.
How did this change? You mentioned that it brought in some unusual books,
It did.
But do you see that there has been a change in training of, say, scientists?
I wouldn't put that all in
Right,
the count here, but
right.
as we take a longer view.
As a longer, exactly.
I think that's right. So one of the things that I found really fascinating in doing the work for the book was looking at what was it like to be trained in, say, quantum mechanics at the era when these folks were themselves, say, college students and doing their graduate work in the 1950s and 1960s. And by and large, there was an enormous accumulation of very effective ways to teach quantum theory, but to teach certain aspects of quantum theory, certain styles of teaching quantum theory. So the students got very good at solving incredibly hard problems. The problem sets were not easy by any measure.
Right.
What was kind of bled out, or really de-emphasized during this 1950s and 60s, mostly in the U.S., to some degree elsewhere, was the kind of more open-ended, speculative, interpretive, we might say philosophical approach. The what does it all mean stuff. And because, whether it's entanglement or even much older paradoxes like Schrodinger's cat or all these kind of strange-sounding ideas, the uncertainty principle, there's something unlike what most of us take for granted every day that seems to be going on with this theory. It's in my opinion, a beautiful theory, quantum mechanics, by now exquisitely well tested, and yet it's not like it's sort of just what we expected, right? It still has these deeply, I would say, deliciously counterintuitive features to it. And in the earlier period, before World War II in this country, it was common for even very advanced students to really have to practice, to write essays explaining what they thought the kind of quantum weirdness was all about, give their own interpretation of the equations. They had to learn the equations, manipulate them with great agility, but also step back and kind of put into words, what do they think is going on here? What does this mean compared to what we might have expected otherwise? And then during fast forward a few decades, by the 50s and 60s, that part had really just dropped out. It's not in the textbooks. It's not in the exams that we now find filed in various archives. It's not on the homework assignments and so on. And so that period, which is when these folks were themselves going through training, what it meant to be a physicist, was had certain kind of parameters, certain boundaries to it. And what happened when that whole system kind of cracked or went through a real moment of deep change with the job crunch and the fall in funds and the real kind of a real pivot point around 1970 was that additional means of trying to be a physicist kind of crept back in. They weren't invented whole cloth. In some sense, they were almost a return in the style, in an emphasis, to the way students had trained at MIT and Caltech and the best places, Berkeley, in the 1930s. There was space again. It was considered legitimate, a place at the table by the time the 1970s or early 80s. By that time period, it was considered legitimate again to wonder about the kind of quantum mysteries, not at the expense of learning how to manipulate the equations and do very careful discipline work, but that was somehow not the sum total of manipulating, of learning quantum mechanics. So we see these kind of sea changes. And the hippies are at that, they illustrate a transitional moment. They don't cause by themselves by any means what comes later, but they show us that kind of unstable moment of transition where what seemed obvious in one era is clearly about to give way to a different set of assumptions of what it is to be a highly trained, smart scientist. So when we get to places like MIT today, all over the world, not just MIT, there are courses in the foundations of quantum mechanics. There are whole courses in the interpreting these equations. And not just manipulating them. Both are really important. There are exciting developments in areas that had once been deemed not science. Not in 1600, but in 1965. In relatively recent times, areas that had once seemed simply beyond the pale. And I don't mean ESP. I mean this. Just trying to what does it mean to wonder about quantum entanglement? Right? That's now front and center. And I'd say, thank goodness. That's a good thing.
Yes, absolutely.
And more broadly, there's a space for a kind of interpretive or open-ended, more speculative approach to physics. Not all or nothing. Now we might say, a broader spectrum, and that's real physics too.
I see. That's good. And then your department adds some other dimension to this, correct? Which seems like it should be essential everywhere. The Science, Technology, and Society program at MIT. Could you tell us a little bit about that?
Sure. So MIT's program is among the earliest to be founded, at least in North America. It's about 40 years old. And so we have a collection of faculty, we have undergraduate courses, graduate program, we train PhD students. And it really is an effort to understand, in some broad sense, how do sciences and technologies, engineering, how do they emerge from the world, the messy worlds of science and politics and culture, and how do they remain embedded in them? And so whether that's a concern to unmask the kind of hidden biases, as in earlier eras of, say, scientific racism, as we mentioned before, very stark examples of what looked like kind of best science, in fact, was clearly reflective of a set of other societal assumptions. Or indeed, say, like the Hippies book, or many of my colleagues' fascinating works, to say even work that we might hold up to this day as kind of illustrative or luminous examples of science. Again, that's not coming from outside of the world. One way I like to think about it is to say, if all science is embedded in politics, that doesn't make the science wrong, but it does make us wonder about choices that are made. Why was that scientific question prioritized over others? Why were those people able to pursue that then and there? And that could be for, frankly, perfectly good, understandable reasons. But the science doesn't just happen on its own. An example that I've been thinking about for a different book project that's still in the works is about Einstein's general relativity, a crowning achievement, I would think, of Einstein's own career of the 20th century. I think it's just,
and of science.
And of science. It's just gorgeous. And at many, many moments over the past centuries, now coming up on its 100th anniversary in 2015, this seemingly otherworldly, sort of austere, ivory tower seeming kind of set of ideas was just thoroughly enmeshed in sometimes the messiest of the 20th century, from the trench warfare of World War I to the rise of the Nazis to nuclear weapons development in the United States to concerns about Soviet missiles. It was part of the world. And so for many, many years, one of the most quantitatively accurate tests of general relativity, one of the reasons we had most confidence to believe these other, again, so strange-sounding ideas about warping space-time and whimsical-sounding things, that came from very sensitive experimental tests performed at a defense laboratory that was aiming to figure out early warning of incoming Soviet missiles.
Is that Lincoln Laboratory?
Lincoln Laboratory, yes. And so as a kind of byproduct, at first unanticipated byproduct, of trying to get very, very elaborate radar systems to scan the horizons, to watch for incoming missiles, to maybe have half an hour of warning to evacuate cities. And this is the messy world at play. This is the Cold War nuclear age. that in the process of fine-tuning those radars, calibrating the whole system, it turns out there were very few missiles coming over the horizon. There were zero, thank goodness. So they couldn't just say, well, we'll wait for the next 50 missiles and see what we see, because they weren't coming, thankfully. But other smart people realized that some of the planets in the solar system would look a lot like a missile at that stage of its trajectory. If you could send radars to the planet Venus, then you could do target practice and figure out how this whole complicated, state-of-the-art, highly high-priority defense system is going to work. And so, as a byproduct of trying to fine-tune a defense system to worry about if and when Boston or New York City will be incinerated in nuclear holocaust, I mean, that's just the world we're coming from. We have emerging from there in very ingenious and creative ways a sort of beautiful test of general relativity. So I go into that as an example of, this is not, so even a theory is like seemingly sort of pure abstract general relativity. It's of the world, and we gain knowledge of it in the world, and sometimes because culture and politics of the day prioritize this system over that. So that kind of work is what my colleagues, my students, and I are really fascinated by in MIT's STS program.
Right, and it sounds like a wonderful program, by the way.
Good.
So I'll make sure that we're linked to it on your page. I'd like to ask you, as we're winding down here, you've written a great number of books, a great number, and I will show some when we on the video.
Okay.
But first of all, do you have a favorite or two? And then I would like to talk about what you're working on now.
Sure. Well, of course, they're like children now. You can't pick favorites. But I will say, I mean, working on the Hippies book, every single day that I got to work on that was just fun.
How about that?
It's a great, great privilege to be a university professor. It's a wonderful job description. And on top of that, I mean, even a step or two above that, certainly for me, was getting to kind of immerse myself in that world, and that just every moment of that was really it was a joy. My first book I have a different kind of sense of affection for. Was trying to understand how did Richard Feynman's very quirky, sort of idiosyncratic approach to quantum physics become how sort of we all see the world today. We in physics all see the world, and that again was. It was a great privilege to get to work on that. So they've all been fun.
Well, I'm glad, because you produced a great number of them. Very readable, very interesting. Good. The public appreciates this very much because we need to hear from the scientific world. You are working on some rather interesting things just now. Could you tell us a little bit what you're up to?
I'd be glad to. So
this is your physics work now.
Right. So. One of the things that I get to do a lot, which is really fun, is to think about the very earliest moments of our universe.
We are all thinking about that, yes.
Yeah, who doesn't? I know. But it's a wonderful time to be working in cosmology today.
Yes,
it really is extraordinary. And so one of the with my mentor and my very dear friend Alan Guth. We have a whole group, a kind of gaggle of students from undergraduates through graduate students and postdocs. It's a remarkable, thriving group, and it's a real privilege to be able to work with them and with Alan. And we're really curious about, given what we know about matter at its most fundamental, that obeys quantum theory and the uncertainty principle and all these kind of abstract ideas, and given what we know about Einstein's relativity and the stretching and warping of space-time, can we kind of fit together a coherent picture, a coherent story of how our own universe could have and maybe actually did behave in otherwise impossibly distant kind of conditions, very high energies, very dense states, not like what we'd find ourselves in today. And if so, could we make predictions? If that had really happened 14 billion years ago, what might we see today? What should we see as remnants of that in the sky and the distribution of matter? And roughly speaking, it matches unbelievably well, beautifully well. Very specific quantitative predictions now about little wiggles in the distribution of light from the earliest moments that we had light streaming to us after the Big Bang, again, approximately 14 billion years ago. And we can now, satellites and ground-based and balloons, all these instruments can now measure this cosmic microwave background radiation to amazing precision. And there really are bumps and wiggles. There are patterns in that. The light does not all have exactly the same energy at every place in the sky. It has almost exactly the same energy and tiny little fluctuations away from that central value. And the patterns of those deviations match unbelievably well to our ideas of where those bumps should have come from, which brings us right back to the heart of matter at its most fundamental. It's a wonderful time to study these things.
When is your book coming out? This one that you're doing with Alan?
With Alan, well.
And, I should mention, by the way, who is famous for developing the inflation after the Big Bang, which is still full of problems, I suppose, but was, I guess, the best answer, right? They thought.
I would say the cup is more than half full. It's
Okay.
half empty, but it's certainly it's a remarkable set of ideas. So Alan and I began working with this group of students about 3 years ago. And he's been teaching a wonderful undergraduate course in early universe cosmology at MIT for many years. And I began writing little primers to help our students. We realized let's put these together. There might be a book there. So when will it come out? No time soon. It's very much in progress. But it's a great pleasure to work on it, and we hope to bring it together in the next year or two, we hope.
Well, you do a lot of very exciting things. So I think your mind must be busy at all times, 24/7. It's very inspiring.
Thank you.
And I have to stop here, but I really appreciate your talking with us about this. I wish you the very best of fortune for it's such a huge contribution to the general public.
Well,
thank you.
Thank you very much.
And I will stop here and let you talk to some people.
Wonderful.
And thank you again.
Okay, well, it's thank you so much for sharing with us tonight.
Sure.
I'm about halfway through your book, and I have several questions, but I'll just start out with one. I think you wrote a piece a couple months ago in the New York Times saying that Bell's theorem was going to be put to a new test.
Yes.
I'm just wondering if there was a result from that experiment yet.
No. We haven't run the experiment yet. Mostly goes back to what we were just talking about. Mostly we need money. Experiments are expensive, as I'm learning. And so so my students and colleagues are busy trying to flesh out the very specific plans, first of all. So which objects in the sky should we be focusing on, which quasars, for example, among the million that have been cataloged by astronomers, what ones satisfy these very particular constraints to make sure they have they weren't able to talk with each other in the history of the universe. And that's really fun, but still work that goes. As well as saying, this is expensive, we need some more resources. We write grant proposals and all the rest. So with luck, we could do the first round, a kind of pilot test, perhaps maybe as early as within the year, or maybe a year and a half. And that would be a kind of proof of principle experiment, looking not at very distant quasars, but at nearer stars in our own galaxy. So that makes things a lot easier. It wouldn't be a full test that we envision, but it would show that we could do it. And then, with more money and more time, we'd love to mount the full version, maybe by 2017, 2018, where we'd actually be shooting these entangled particles between islands in the Canary Islands off the coast of Africa, approximately 100 miles apart. And then at the same time having telescopes focus on these very distant objects, these quasars, to determine what aspects of those earthbound particles we want to measure. And so we want to use the stars, or very distant objects, to help determine what properties of that light, those entangled particles, we actually subject to test, and then see do the kind of quantum predictions still get borne out. So it's enormously fun to think about. And it just takes a little more time and money. So
You probably have to go into this without any bias, but what do you think you're going to find?
Right. I have plenty of bias. So I expect we'll find exactly the predictions of quantum mechanics. And that would be a great thing. I mean, that would be really closing down as much as my students and I argue, as much as anyone could in our universe, closing down kind of rivals or alternatives to quantum theory, which are not always sort of aesthetically pleasing alternatives, but that are also not ruled out. They really are logically still in play, even given 40 years of very clever tests of entanglement along the way. They've always been subject to these so-called loopholes, every known test so far. And that's not just a problem for kind of philosophy. It's if these rival theories that are not quantum mechanics if they're still viable in the world, then this whole machinery that we were talking about a while ago about quantum encryption is at least in principle vulnerable. It might not really be in practical terms, but part of the appeal of quantum encryption is that it should be guarded by the laws of nature, not just guarded because it's hard for computers to scramble certain numbers as a kind of practical matter. But the real beauty, I think, or the real pleasing aspect of quantum encryption is that nature behaves this way, and that disallows anyone, no matter how clever, to hack into your signal, right? And that sureness, that foundation, rests upon quantum mechanics governing the world, and not some of these kind of woolly-sounding alternatives. Those alternatives, though not pretty, are not ruled out yet. We'd love to really say we've put the squeeze on them. On the other hand, look, if we found convincing evidence that quantum mechanics wasn't describing the world on these scales, then of course that's even more exciting. Then who knows what goes on? If I had to place money, I'd say the bet is quantum mechanics really does describe the world, and we'd hopefully show that on a grand scale. So, yeah.
I would just say this. In your book, you mention about the whole kind of pragmatic shut up and calculate mentality, and how this was, in a sense, maybe not intentional, but just kind of a naturally born reaction to that based on the time and the events of the times and the kind of thinking.
Right.
And I would think that was courageous. I mean, these students who have a reputation that they're cultivating, I'm assuming that to go out on a limb and look at something that may be considered science, pseudoscience, or something like that takes a lot of courage, but also might be something that's critical in terms of really finding deep truths. What do you see that's happening today that might be like that, where people might be subject to a lot of criticism, but maybe they're just being very courageous?
It's a great question, and I wish I knew in some sense that I'd know what to go, direct my own students to what to work on. What's going to be the next big breakthrough that everyone is dismissing today? The fact is, I don't know. I take heart in the notion that there is a much broader sense of what counts as kind of legitimate science, or say just in the case of physics, a much broader sense today than there was as I read the historical record several decades ago. And again, that sounds like today's good and yesterday's bad. I mean, there was amazing progress made in the 1950s and 60s, tons of Nobel Prizes. People learned things about the world then that we still take for granted today. So it's not that this is all good or bad, but there are choices get made. There's styles that become kind of cultivated. And certain kinds of questions can flourish maybe more easily in one sort of regime than another. And I think we're in a time period today where there's recognized room for a variety of approaches. That doesn't mean we're all going to on the right path, right? Most of us will be wrong most of the time. But I think the boundaries of someone saying that's simply not science, there certainly are boundaries, but I think there may be a bit broader, a bit looser. Friends of mine work on ideas today that really do that can sound pretty outrageous or silly or who knows what. The multiverse, alternate universes, extra dimensions of space that no one's actually ever seen any evidence for. I mean, on the face of it, those could sound as ungrounded or as metaphysical, or you name me, you supply your adjective you'd like, as what had once passed for merely the occult. That doesn't mean that stuff's right today. It does mean, though, that there is room for real smart physicists to study that and to publish in the leading journals and to teach courses in that. So that's why I think there's a kind of broader range of what counts as legitimate these days. There are limits. Are we still missing things at the boundaries from our own blind spots or biases? I imagine we likely are. I'm sure I am. But I think that kind of very characteristic moment of the shut up and calculate, I think there's plenty of that kind of science today which can lead to very good and important science, but that's not sort of the only game in town, the way I think it was more or less dominant earlier on.